Hello, community. So great that you are back. Let's talk about the latest in Neuro-Symbolic artificial intelligence. At first, welcome to my channel Discover AI. We have a look at the latest AI research paper. And here we are. This is here November 24, 2025, Chain of Visual Sort, teaching vision language model to see and think better with continuous visual token. And whenever I see UC Berkeley, UCLA, and Panasonic AI Research, I think, hey, yeah, Berkeley, I have to read this paper. So let's have a look. Now, it is interesting because they go here with different ideas. No? They have here the counting here in the image, then they have a relative depth estimation of the image, and they have a scene understanding here. So you have a segmentation mask here, and SAM3 is beautiful. But enabling the model to capture the fine-grained relationships across the vision-centric tasks, like counting or the depth ordering or the scene understanding, all of this is done without relying on external tools. And you might say, hey, where's the symbolic AI? And I said, okay. And if you look here, look, this is here the training pipeline. So we really go here with a segmentation mask, with a depth mask, with an edge mask, and then we have Dino. So we have really 4 different elements that we try to extract as much information possible from this image. And then we have a loss function and optimization, everything that you know. So the authors use 4 vision models here to supervise here their methodology to learn each ability. So the first, as I told you, we do have a segmentation AI. This gives us here the position and the shape of objects in the image. Then we have a depth AI with a pixel level depth information. Is the chair standing in front of the car or behind the car? Then all the edge information, so the geometry level details here. And Dino gives us here the patch level representation of the images for the semantic information. So each group here, visual token, corresponds here to a perceptual expert. And what we do, the vision language model is asked to predict these continuous visual tokens from these 4 engines within its reasoning chain. Okay, and then we just have backpropagation, the alignment with the model, internal and latent representation with the expert guidance, and you understand exactly what is happening. And I was quite interested till I saw here the training loss function. And look, they have really a joint loss function that is defined here as the segmentation visual loss, the depth visual loss, the edge visual loss, and the Dino visual loss function. So I don't know if this is really the way forward. Hey, UC Berkeley, come on, let's be a little bit more creative in your intellectual level. So this is basic. Okay, so if you want to learn about Dino, by the way, I have some videos here on Dino just 2 years ago. This is an old technology. And although here UC Berkeley did here a beautiful chain of visual sort homepage where they explain everything, and they have the code and the Hugging Face model and the data set and everything, and here's the project base, it is not really convincing that I would say, I make a video and I would like to show you this research. So you might say, any other idea for really the latest in advanced AI for vision? Well, I'm glad you asked, because we have here November 27, 2025 from Qwen 3, the vision language, the technical detailed report, how they did this here. A beautiful abstract. And I started to read, and maybe you already know it. And of course, we have here our vision encoder here, and then we have here beautiful our language model dance and our mixture of expert decoder structure. But you know what? It is more or less the same. No, it is not the same. It is better in every single step. It is a continuous improvement. But exactly this is it. It is an iterative innovation. It is not a breakthrough innovation. So everything they did, they optimized every single step, and beautiful. It has a much better performance. But from a theoretical point of view, was there some amazing new idea? Well, if you look at the performance data here for the 2 billion, 4 billion, 8 billion, and you compare it with a GPT-5 Nano, you see, okay, it is better, yeah. And if you compare it in the knowledge domain, in the reasoning domain, the alignment for the coding and agent, it is great. It is absolutely better than the 2.5. But you know what I'm looking for is something else. I want to go to the other extreme position of visual AI reasoning. Because in my last video here, where we talked about Monet, where we had a visual reasoning now solved not in pixel space, but in a mathematical configuration, this is here not at all here if you want a Neuro-Symbolic AI. This is here an intrinsic neural model, no? Pure mathematics here in the neural network. And I was looking for the other edge, no? What is the other extreme? And you remember I did a video just some days ago here about Agent0 here, University of North Carolina and Stanford University. And they were talking here about a self-evolution of AI beyond humans. And they used here massively tools, Python environments and everything. They said, over there. Of course, this was not a vision language model, but I said something like this. And guess what? When I checked the authors, they published a paper just 3 days ago, and now we have an Agent0 vision language model for an integrated vision language reasoning that is absolutely tool integrated. So we have our symbolic AI integration. So beautiful. Please notice now it's not Stanford University anymore. Now we just have the University of North Carolina, Chapel Hill. And those are beautiful authors. November 26, 2025. This here is the reference for you. So Agent0 vision language is now real similar to our textual agent. The vision language is now a self-evolving vision language agent that achieves a continual improvement through a tool-integrated reasoning, a tool-integrated evaluation, and a tool-integrated self-repair function. And you say, this is it. This is the paper I'm looking for. Because now I can show you Neuro-Symbolic AI in a beautiful form. So here we have it. On the one side, here on your left side of the screen, you have here Muni AI, complete intrinsic model, deep in the transformer architecture. And on the right side, you have now Agent0 vision language with an intensive tool-integrated reasoning, so the perfect Neuro-Symbolic AI model. Let's have a look how they compare. Yeah, Agent0 has here just updated here 3 days ago, the GitHub. You have now here the Agent0 vision language, happened just 3 days ago, already 611 stars. Have a look at the code, have a look at the explanation. It's an Apache 2 license, real nice. Why is it so interesting? Because it has access to the symbolic truth, no? So if the code is right and you get the transfer, the mapping here from the textual complexity to a code complexity right, then you just send it off to a Python ecosystem and the answer is 99% correct because Python does code this in a correct way. So this creates, if you want, a neural interface for logic. And if you want, what is Neuro-Symbolic AI? Now, in my interpretation, I think it is an architectural coupling here of a differentiable perception of our neural networks with a discrete reasoning engine. This is our symbolic part. So if we say this is it, let's see what is the latest development. And let's jump to the results, because if it's not great, the results, we don't waste the time looking at this model. And the authors tell us, you know what, our Agent0 vision language, and they built and supervised fine-tuned an 8 billion free trainable parameter model, achieves the best overall performance among all open source models. And they said, we did it on 2 base models, on a Qwen 2.5 vision language 7B, and on a Qwen 3 vision language 8B base model. And in the one case, we had an improvement of 12%, and in the other of 6%. And plus it outperforms the GPT-4 Omni, maybe you don't even know this, on different benchmarks. So for an 8B model to outperform here a GPT-4 Omni, this is now interesting. Let's have a look. But you know what? Designing here all my videos, I also experiment a lot with code, but also with how do I present you this content. And I also experiment with different visualization techniques and different visualization AI engines. And there's one agent that I wanted to check out myself, and this is here Flux 2. Flux 2 Pro version. And you see here the Flux Playground. You can go there. You have 50 free images if you log in. And I said, okay, I have to do this. I want to see here, because in my last videos you saw Nano Banana Pro. What about Flux 2? So I designed a prompt and I've given it to both systems. And here you have the result of Flux 2. So you see, yeah, the edit is, the prompt was simple, a dense, high-fidelity, 3-dimensional isometric cross-section of 2 distinct AI reasoning engines sitting on a dock technical schematic grid. And then I just described here the Monet configuration with the vision transformer space And here our magnetic vortex structure, where we have here, if you take here the example of a fusion reactor here, our golden plasma stream in the middle as an optimization of the policy optimization. And on the other side, we have our new Agent0 vision language core idea, where I said, okay, we have a conveyor belt bringing in all the new information. And then we have here, if you want, a symbolic AI, a logic AI machine with a lot of different satellites. And one is a Python environment, one can be a Lean 4, one can be a formal solver of any kind, or even in the author's quote here, an OCR repair. You see here there's a little mistake. Or just another Python here for a particular supercomputing visualization, whatever. So this is here what I'm given back here from Huaxiu. This was done here today, on the day recording this video. So you get a feeling how this is now a visualization. But of course, this is just one way. Now, I told you I experiment with it. And if you go now to NanoBanana Pro, and this is here an example here on the official DeepMind Google page for Google Image Pro, like Google did this, but we are doing a little bit more because we are doing this. So now again, here you have now a computer image of our Monet idea on the left side, an intrinsic transformer solution, and a simple working bench conveyor belt solution here with external symbolic calls here on the right side. Our Agent0 on the right side, Monet on the left side. So you see, just giving you this impression how different we are. On the left side with Monet, we are really deep into an optimization of a mathematical hyperspace on our transformer that is really amazing. So we have here, I tried to show you here all the transformer layers that we have. And then in those layers, of course, we have our blue data nodes. You remember the image patches that I talked about here with Monet. And then I told you we do have here a pathfinder. Now Monet is here a path optimization on a real complex hyperplane. And as I told you here, we have a supervised fine-tuning, and then we have a reinforcement learning. But of course, it is not possible to use the GRPO optimization, here the policy optimization, but we had to go with a visual latent policy optimization. And I told you, imagine here this in orange, this is a magnetic flux tube, like here in a fusion reactor, and you want to compress this here to a lava string here. That is really the optimal solution. So you compress further till you have here a real narrow vertex tube with the solution here in the visualization. Look at the other side. This is a, I don't know, industry 20th century conveyor belt idea, no? So what we have external satellites where the intelligence is, like a Python environment. We got here Python executor, over here satellite modules, whatever. So we have here a machine. We have little chunks coming in. Now, the beautiful thing is everything is generated and scanned immediately for mistakes. And if there's a mistake, so if the machine detects an error, so the analysis goes out, Python tells me, hey, I calculated what is in this little patch here. It is incorrect. You have to correct it because the code would be A, B, C, D. So then the machine says error and automatically starts a self-repair module. So this patch is now optimized and we have some beautiful correct patches coming out on the other side. You see immediately that those are two different worlds, you know, how we implement this. So this is here the beauty, if you want, of a real complex mathematical idea in a latent space. And this here is just the workbench. Let's go to the mechanism itself. Let's go a level deeper. So again, on the left side, we have Monet, our latent simulator. And I got a lot of questions from you talking here about, hey, this Gaussian policy optimization of the normal distribution where we have here the probability. Some of you ask me, hey, what is happening here? So, okay, never mind. Very short explanation. So in our continuous latent manifold here, remember this is again our magnetic torso, like in the fusion reactor where we want to compress it further so that we find here the optimal path in this complexity. Let's go with this and then I explain here the right side. So at first, you remember the image in the system's memory here of Monet is actually a cloud of 256 vectors. And instead of maximizing the probability of the token that we have in our LLMs, our new VLPO maximizes now the proximity to the successful sort vectors in the cloud. So this means, let's focus here on our normal distribution. This n mu sigma that you asked me so many times now is simply the Gaussian probability density function that bridges now the gap between the discrete and the continuous world when we look at vision language model. This is an approximation for the continuous world that works amazingly good. So let's have a look. And yeah, pi is of course our discrete world. So this normal distribution is the probability generator. And you know that a single continuous point has zero probability. As I told you here, the probability of the term cat, if you go to a continuous model, is zero. So we needed an advancement over GLPO, and this is VLPO. I explained this in my video, and it treats the vector now as a cloud of vectors. So this means here, our sort is now here normal distribution of probability generator of the vector itself, of a mean and of a certain width, our sigma. So this means so your new sort vector is slightly different from the lucky vector, this is here the plasma vector, that solved the problem yesterday. It now falls within our, if you want, orange magnetic vertex, within our probability distribution, the normalized distribution, the Gaussian normal distribution, so we can calculate now a high probability score and calculate the reward. So what this new policy optimization here, our VLPO tells us is, or it tells the model, the AI model, shift your mean, your mu, closer to the successful trajectory, scaled here by a little variance sigma. This is now, if you want, the distance here in the continuous fluid space of your sorts, not of your word tokens. Okay. So this means, coming back here, VLPO is the algorithm that allows us to learn reinforcement learning to sorts, to vectors, instead of words with the tokens. So this bridges now the gap between the language modeling in a discrete space and a new control theory in a continuous space. And if you say, hey, control theory, there was something in your last videos, yes, of course. When I talked about the cybernetic AI, the cognition or the cognitive tensor field, it was part 2 of the dual manifold AI video. We exactly talked about cybernetic AI, control systems for the AI. So you see, we move in the same direction. Those researchers here also went forward with this idea for the next vision AI idea. Okay, this was just last video. Now we're talking about the Agent0-VL language here on the right side of your screen. So here we have now a discrete symbolic execution. This is so easy, I hardly have to explain this to you. Huh? Let's say here, from the bottom, we have here a little piece of information, beautiful, it is analyzed. And it is analyzed, and you see here a Python, I don't know, algorithm, analyze it here for particular parameters and see, hey, is it working, whatever. If this analyzation is coming back and say, hey, there is a mistake, it automatically stores a self-repair progress. And as you see here, if something is broken here, we have here now a laser welding, and now this piece is now corrected. The right code or the right formula is now inserted, and beautiful. And so we have now in the next step here, the corrected cube of information, if you want. It is scanned again for whatever the text is analyzed, and the code is analyzed, and everything is checked again. And then if it's blue or green or go, beautiful, then we have it. So we do have a self-learning system because, of course, those errors and those rewards are fed back into the generation of our little knowledge cube when they come up here to be analyzed and further rewarded. So we have a self-learning system, a self-repair system, and a self-learning system. But of course, you see, all depends here on the external intelligence in our Python environment, C++ environment, Lean4 environment, any formal solver that you like to use, or any computer simulation that you want to run here on a certain computer cluster, whatever. And the LLM only has to have a semantic function, but does not have to be an AGI at all. So this is the beauty here of Neuro-Symbolic AI. Great. So our Agent0 vision language model introduces what the authors call a self-evolving reasoning cycle that enables to reason, verify, repair, and evolve. Now, reason is simple, no? It performs a multi-turn tool-integrated visual reasoning. The intelligence is in the external tool. Verify. It self-evaluates the reasoning step using here tool-grounded evidence. Repair selectively corrects error based on the verification feedback, so the feedback that comes here from our Python ecosystem, and it evolves, continuously improve here through a reinforcement learning, a typical GRPO reinforcement learning. So you see, discrete space, very well known GRPO. And this closed loop system allows here our agent vision language to achieve zero external reward, self-improvement. So there's no need for any human looking over this. But of course, your tools must be perfect. And the transformation here from a textual information to a code, so that our Python environment can then compute this code, is one of the weaknesses here if you have a AI system that is maybe not perfect in transforming here textual complexity into a code representation for the Python environment. Great. Now, I told you already we have this Agent0 vision language here more or less in two roles. Of course, it is a single vision language model, but you just change here the system parameter and suddenly you have two elements or two identical brothers that perform different tasks. You have a solver AI. This performs the multi-tool reasoning and it dynamically invokes here all the external tools, code interpreter, vision APIs, everything that is available external as a tool for a grounded computation and the visual perception. And then, as I told you, you have the check if it's okay. So you have to have a verifier. And this is, of course, the identical vision language model, just with a different system prompt. And this verify validates now the intermediate reasoning steps through generative critique and tool-based feedback. So you get a critique, says, hey, everything was great, just this function here, there was a little bit of a wiggle room. So I would suppose if you use this Python code, this would be a better code sequence. Generating here fine-grained reward signals and repair instruction coming already back from the vision language model, just to be self-learned and self-optimized here by the system. Now, you know I'm just experienced here with my Nano Banana Pro a little bit visualization. So let's have a look at this. We all start here with the input. So here you have images coming in and pure text. No? These are two input data streams that go in here, and here we have the solver. The solver is now trying to do here, based on the text and the images here, a visual reasoning. And it puts out here little tiny lower complexity cubes where we have here the first step of the visual reasoning, the second step, the third step. So this is here a chain of visual reasoning complexities. So we do have sequential data blocks that is coming out here, beautiful. But of course, the real, if you want, intelligence here is a little bit in the vision language model, but for every complexity, it just goes out here to a Python, let's say a ecosystem, a sandbox, whatever you have, or any formal server. It just converts the problem into code. The code is transferred to Python. Python calculates it, optimizes it, uses here the code LLM intelligence, so the intelligence lives here, and brings back the solution. And then this machine is just welding together our little knowledge blocks that come out now here on this conveyor belt, or magnetic rail track, sorry. And then we use here an identical copy here of this vision language model now as a verifier gate. Because you want to make sure for the self-learning process that no mistake happen. And if a mistake happen, this verifier gate will detect it, will identify it, will say, hey, there's in line, or in the argumentation here, the third box is containing an error. So what it does, it finds it, it analyzes it, it provides a solution, it has the same complexity like here. You see, this verifier gate is connected here also to the Python sandbox, to the intelligence. So this is a self-correcting machine where I would say maybe it would be a good idea to have here not the identical vision language model here, like in the solver, because, yeah, whatever, the authors went with identical brothers, great. So we have identified the error, provide a solution. So what's happening? Now the output is going back here at the self-repair feedback loop here to the solver, and now another little knowledge box is welded together, and you have here a self-analysis, self-repair system that has here, of course, and you can reward this if the machine says, hey, this was a perfect little knowledge box, a little visual knowledge step in the reasoning process that we have here. Then you have a high reward, and if it goes back, yeah, of course, reward goes to 0. But let's say if it's not going back to the repair part, but if it's going forward, it was just a perfect little box, then what's happening here, the success path is you want, we have, say, yeah, we generated something that is great, that we want to continue to learn on. So now we go into reinforcement learning. You see, this is a solution I want to remember. I want to strengthen my AI system. So here you have the optimization engine, the reinforcement learning. Yeah, I said build a turbine, real nice done. So we have here the classical reinforcement learning GRPO. We have here update of our nabla J function. This is everything that you know. And then we have this, and of course it optimizes now also our solver care unit, so our generator. So you do have a repair loop, and you have a self-learning loop, whatever was great, whatever worked, as here a positive feedback, and you have here a reinforcement learning loop here on the outer edge, and on the inner loop you have the repair loop. Yeah, this is what I tried to build here with my commands here on Nano Banana Pro. And if you want, here is a little bit additional information here. Yeah, as I told you, the reasoning process here is, of course, the classical discrete space. This means reasoning here as a partially observable Markov decision process. So this means this is our classical system. This is here just what we are known, that what we experienced every time. But depending on how much Python intelligence you put in there, or how many tools, how many intelligence tool, you could have another box with Lean4, another box with a pure formal solver, another box for your particular medical database, whatever. You see, everything is here in the symbolic AI here that is more or less here determined, and it is not an autoregressive predict the next token machine like our VLM. Okay. So, yeah, there's another real nice benefit in the order to tell us, hey, you can use Agent0-VL because it generates a reward. You can now use this only as a module. This is maybe only a single process reward model for some other vision language model, and it works great. Perfect. And now I looked at this and I said, okay, now if I want to ask you a question. Where does the AI reasoning happening if we look now at both engines? Again, remember, left side we have Monet, on the right side we have our agent, zero vision language. Now with Monet we have a continuous latent recurrence and an implicit model. So this means the mechanism is simple. Monet fundamentally alters the transformer autoregressive loop. Instead of predicting here the discrete token, it predicts a continuous hidden state that are then fed back as the inputs. Our Agent0 vision language is a discrete tool-augmented state space with an explicit model. The mechanism is as follows. VL models here the reasoning as a partially observable Markov decision process defined by our classical tuple, and the action space includes here the discrete tool calls to Python, OCR, Lean, whatever. In Monet, the reasoning is treated as a data compression. So the model compresses here in a highly intelligent way with a mathematical algorithm a sequence of visual operation into a dense vector path in a highly multidimensional mathematical space, relying here on the manifold hypothesis that I explained in my last video, simply meaning that the visual state lie on a continuous lower dimensional manifold. So we are lucky that we don't have to go to the complete search complexity of this space. Agent0-VL, the reasoning is treated as a program synthesis and verification step. So this means the neural network itself, or VLM, is not a physics engine at all. It is just a controller for some external deterministic engines that now calculate the result. You see here, what I called here, now our LLM or our VLM is just a semantic operation, but it is not home of the primary intelligence. This is outsourced. Technical explanation for Monet would go like it exploits a high-dimensional vector space of the vision transformer itself, and the reasoning process is now mathematically modeled as a trajectory optimization problem in this space, where the model learns a transition function that mimics a visual transformation, like our affine transformation for the rotation or the attention masking for zooming in on a badge here, without rendering any pixels. There's no pixel space. On the other side, our Agent0-Vision language is a discrete tool-augmented state space. And the explanation goes, the reasoning state encompasses here the text context and the explicit output of all the external tools that come back like a RAG system. So the model does not simulate the result at all. It holds the inference run. It executes the code or API calls or whatever you have. It then concatenates the deterministic output of those elements like a Python environment to the context window for the prompt that goes into the LLM or VLM, and then we resume generation and operation in our autoregressive predictor next token exercise. So you see, I just want to show you, you have two extreme, completely different models. Whatever model you choose, you have unbelievable opportunities. No? On the left side, you have Monet. On the right side, you have Agent0-Vision language. They're complete different beasts. But let's look at them from an engineering point of view. And you see here, yeah, of course, Nano Banana Pro. Look at this. You just see, and I tried to make it in a visualization that you see Monet here on the left side. No? What you have? You have a vision transformer memory space, which is now a continuous vector space, where we have our image patches, you remember? And those image patches are now here the input to our supervised fine-tuning and our reinforcement learning VLPO optimization run. So we do build a complete new latent space, gradient flow, temporal dynamics, everything goes in here. And this is really, if you want here, a really advanced mathematical system with a high complexity. But here the intelligence is really given here by this teacher-student model, as I've shown in my video on Monet. On the right side, this Agent0-Vision language core in the symbolic space, this is hardwired. No? This is, yeah, so we have here the symbolic reasoning plane, then we have the rule-based systems here. Everything is connected here, directly connected. Then we have here, I don't know, this is our OCR, or this is our Python environment. So engine and engine and engine and command and linear chain and beautiful, everything is done. And okay, let's analyze this here. We have a Python runtime and we see exactly the code tells us, given that we have a code LLM on a Python environment, okay, this is here incorrect, correct the code. Everything is more or less really coded. So we do have a symbolic reasoning and logic gates that are here steering here our logic stream. If the code tells us, hey, there was a mistake, or our OCR API tells us, hey, I can't read this, or this is incorrect, no, if we have an error, so this is here our scanning unit, we try to identify the error, find a solution for this error, feed it back, and then run the system again. But if the self-repair was successful and we have a green light, then yeah, it is outputted as a result. And we have here, of course, a reinforcement learning processes that runs back through here, the channels here, the fiber optical channels, and improves, self-improves here this AI system, of course, given the complexity solution of the Python runtime, given the complexity solution of the VLM itself. If it's a 7B or an 8B model, you are, of course, reduced to lower complexity topics. But you see, it is a complete different beast. And this is what I just wanted to show you. But you can now choose. Do you want to go with a Neuro-Symbolic like here? Or you want to go really have a deep dive here into the next generation here of pure vision engines here based on AI. But this will be a complete different architecture, like I've shown you in my video here on money. Examples. Yeah, let's do some examples. That is a great idea. So here we are. So they give you here a question. What street is indicated by the sign on the pole near the center bottom of the image? And you have here an image here of a street with a building, and there's a little sign, you can hardly see it. And they give us here 4 options, Michigan, Michigan, whatever. And they say select the correct answer. So what happens? The model is now syncing. The task is to identify the street name display on the sign located near the bottom center of the image, and yes. So it says now, okay, identify the task. I know what I have to do. I have to do some cropping here on the visual data. So what it does, it calls here a tool, a particular tool. Somewhere you have this beautiful, calls all the subroutines, says, hey, crop and zoom the image, the crop coordinates, the zoom factor is 2, whatever. Just read the text, because in the original image I could not read the name of this street. Bring it back, and comes back, and then the LLM tells us, yeah, I have now here, if you want the reg system, it tells us now, okay, this is Michigan Avenue. Beautiful. Done. Simple as hell. They give us here also the system prompt for the solver. I told you those are 2 brothers. Those are identical machines. This is here the system prompt for the solver, and this is here the system prompt for the verifier. Really easy, simple principles, simple checks. Now let's have a look at the performance of those systems. Now you see the last 2 lines, you see here the Agent0-7B model and the 8B model. Now please note, this is important, it is not that the jump from 53 to 65% is just the 1B model difference, because the 7B model is based on the Qwen 2.5, and the 8 billion Agent0 vision language is based on the Qwen 3 model. So careful, this is the 2.5 improved model, and this is the Qwen 3 improved model. Now you have here the Qwen 2.5 and the Qwen 3 in the original habitat, and now you can compare if it's really that amazing, if it was worth here all this. And you see it depends heavily on the tools, on the code that is generated for the tools when a vision language model calls a particular set of tools, their sequence of the tool execution, and everything about code LLM and everything about the external complexity interwork. You can decide that you want to go for this Neuro-Symbolic AI. But just remember, you have so many unknown performance components if you use 4 or 5 tools, and you can never be sure that the VLM decides to use the right tool at the right moment with the right amount of energy, at the right amount of time, and the right complexity reduction. Okay, great. So this is here the result. But I just want to give you this feeling. What is it? So this Agent0 doesn't just see the image via the tokens, it acts on it only via code. So if the agent outputs here discrete text blocks, hey, use a tool, use the crop tool, give them the coordinates, burp, these are the coordinates. This is just a symbolic command. No, this is nothing visual. This is a command that the system holds, execute here the crop tool use, and feeds the result back here to the context. And it has simply learned this, because guess what? Our Agent0 vision language 8B model had a training and had generated here a supervised fine-tuning data set for this training. And this 7B model, 7B or 8B model, saw thousands of examples where if we have a fuzzy text, like I showed you here, the street sign in front of the building, and the read request, like, hey, tell me which street is it, then it has to use the crop tool. So you see, this is a pattern that it learned in the supervised fine-tuning run. And the vision language agent creates the code because it was in the supervised fine-tuning training data to treat any visual ambiguity as a grammatical prompt to start speaking in the Python syntax. So it bridges here, if you want, the gap using here a massive pattern matching engine of the transformer. And if you say, hey, how was the supervised fine-tuning training data generated? Who did this? Well, of course, guess what? We had a huge teacher vision language model AI system that broke it down into reasoning traces, and then our little 7B or 8B Agent0 language model as a student model tried to learn from the teacher model. The final thought, some personal comments. I see money and this beautiful intrinsic, highly complex mathematical optimization engine for a path in a crazy mathematical space as an internal physics simulator. What data do we have? A continuous fluid vector. What is the process that we perform? A simulation. What is the analogy? I thought, imagine a tennis player, and a tennis player visualizing now the ball trajectory. So they don't do the mathematical calculation like a calculator, like an external tool, like a Python environment or C++. The tennis player just imagines in his or her brain to simulate the physics in their motor cortex, but this motor cortex is nothing else than the latent space of money. And the math engine is then a new policy optimization, and it is optimizing the continuous curve of the tennis ball or of the virtual thought process. I hope this analogy gives you an idea. There's no calculation. This is just here. They don't do the math. They simulate the physics in the motor cortex, in the latent space. And I told you, this is here the beauty to build this space. Now, on the other side, today's paper here, Agent0 language, is an external logic controller. So the data type is simply a discrete symbolic token, either text, JSON, whatever you like. The process is a code execution. And the analogy is simply a physicist calculating, now sitting down, table calculator, doing all the calculations of the ball trajectory. So they measure the wind, gravity should be a constant on planet Earth. They write here a formula, Python calculates and solves this problem. And then we have here the engine is, if the optimization, the alignment is here a GPO. Optimizing here the sequence of discrete steps. So you see, they're complete different machines, complete different beasts. Both are vision language model. Both try to do a vision chain of thought thing. But the way we implement this on a technological level is completely different. And I think money is just off the rails, and I love it. So, the latest simplification for today, this is the end of the video. I think money is trying to build a better brain that implicitly understands physics, sees the images and understands here intuitively, given its training data set. And if you're a tennis player, you have seen how you have played 1,000 hours of tennis. No? You know exactly the trajectory of the ball. You don't need to calculate. But Agent0 language is trying to build a better user that explicitly uses tools to calculate each and every step and therefore be on the right side, not on the autoregressive part, but really on the calculated result in order to compensate for a weaker intelligent brain. I hope you do agree with this statement here of mine. If you find it here in any way offensive here, well, you see, this is just another framing you can do, and you try to understand, hey, what is the capability? What is here the strength? What is the power of a vision system? And you can build so many variants of vision system. I hope you have a brand new idea. And hey, why not comment here in the video if you think you have a new combination or you have a complete brand new idea how we can build the next vision language model. I hope you enjoyed it. I hope you had a little bit of fun. If you like it, hey, why not subscribe, become a member of my channel, and I hope to see you in my next video.